We today are going to continue with 811. So again, the notes that you printed off yesterday, we are going to finish up today. Okay, so we are starting with kind of like the second full page of notes. Look at my screen. That's what your notes page should look like. If you didn't have a printer, then go ahead and continue to take notes on a blank sheet of paper, but I would definitely recommend that you pause and go ahead and kind of draw out rough sketches of these graphs, because we are going to pick apart the general trends today, so your notes would not make any sense without the pictures and equations for each graph. Okay, so it says on day 2, below are the correct graphs for 8 polynomials. Use the graphs to answer the following discussion questions. Okay, so we have 8 graphs, but the discussion points are at the bottom, so we're just going to go one by one. I'm going to try to color code the best that I can, and we're going to start to make some sense by the end of this lesson as to how we can graph these on our own. So the first question says, I'm going to do this question in yellow, which of the 8 polynomials are in standard form? Okay, so, and then it says which are in factored form. So remember, standard form, we are looking for terms linked together with plus and minus signs. So if I go ahead and go up to my polynomials, I can see all 8 equations. So I'm not even looking at the graphs for this question. But I see this first one on the left is in not in standard form, but then P2 looks to be factored. P3 is in standard form. Okay, P4 is in factored form. Whoops, and I'm not going to highlight the whole thing. I think I'm just going to do yellow. P5 is in factored form. Now you might see that X out front, but really I think it's okay that we go ahead and put this in parentheses because there's just no constant being added at the end. P6 is in standard form. P7 is like P5 in that we can go ahead and put parentheses and say that is another factor. And P8 is in standard form as well. So P3, 6, and 8 are going to be the answers to our first question here. So we have P3, P6, and P8. Now, all of the other ones, hopefully you would agree with me, were in factored form. So we have polynomial equation 1, polynomial 2, polynomial 4, 5, and 7. All right, so that is a great review of standard form versus factored form. Okay. So, number 2 says the degree of the polynomial, which we talked about that last lesson on day 1. So, the degree of a polynomial in standard form, so we're talking about standard first, is the degree of the monomial term. Monomial means 1, so the term with the highest degree in the function. So for example, they're giving us an example looking at polynomial 3. They said if our equation is x to the 4th minus 21x squared plus 20x, the degree is said to be 4. Now don't just always look at the first term because sometimes the exponents aren't written in descending order. So let's go ahead and look up at the functions that we highlighted in yellow that are written in standard form, and let's find the degree of those, and then we'll go back to factored form. So P3, okay, let's go ahead and find our highest term exponent, which is 4, so this is a 4th degree polynomial. Okay, on P6, find the term with the highest exponent. So once again, we see x to the 4th, so that's a 4th degree polynomial. Now on P8, I always look at all terms just in case it's not written in descending order, but again, this is a 4th degree. We look at the exponent, not the coefficient that is in front of it. Okay, so then if we go back to number 2, now we are going to look at if the polynomial is in factored form. okay, we are looking at the number of linear factors that exist in the factored form. So if we look at P1, someone might be tempted to say this represents a degree of 2 because there are 2 factors. But what do we have to be very careful with? This squared. So what does that really make this polynomial? X minus 2, times x plus 5 times x plus 5. So how many linear factors are there? There are 3, so that would be a third degree. Okay, now please note that if you put a constant out front, which a constant is like a number, okay, so if I were to put like a 3 here, this is still a third degree. A linear factor has to have an x in it, has to have a variable. Okay, so if I put 3x, this would turn into a fourth degree. Okay, that's maybe a place where people might get mixed up. So let's return up to our functions and decide the degree of everything else. I'm going to write that in blue. Okay, so on P1, we already said there are 3 factors. Another way people look at it is you can always put an exponent of 1 on a factor if it's not there, and you can just add the exponents. 1 plus 2 is 3. On P2, we ignore the constant. Okay, so how many linear factors do we have? We have 1, 2, 3, or you can add up 1 plus 1 plus 1. The degree is 3. On P4, we have 2 factors here, 1, 1, 1. So 2 plus 1 plus 1 plus 1 is a fifth degree. That is a fifth degree polynomial. On P5, okay, this is indeed linear, a linear factor because it has an x, okay? So notice the difference. It's not just negative 0.1, it's negative 0.1x. So we have 1 here and we have 3 here. So if we would write it all out, we would have 4 linear factors. So this is a fourth degree polynomial. And then finally on P7, again, this is a linear factor because there is an x. So we have 1, 2, 3, 4, so it's a fourth degree. All right, so we've established how to find the degree of polynomials. Okay, now we are going to look at end behavior, okay, or the direction at the ends of the graph. This whole chapter, we are going to mention this a lot. So if end behavior comes up, that means what are the arrows doing at the very ends of the graph? Okay, now yesterday I talked about increasing, decreasing. This is slightly different because with end behavior, we don't look at the graph from left to right. We just look at the direction of the arrows, which actually makes things kind of easier. Okay, so let me start from the beginning on question 3. It says the end behavior or the direction at the ends of the graph will either be the same, okay, meaning that either both arrows are pointing up or both arrows are pointing down, okay, or it could be opposite. One arrow's pointing up, one arrow's pointing down, or vice versa. One's pointing down, one's pointing up. Okay? Our goal is to think about patterns and trends to see if looking at an equation, we would be able to predict or come up with the end behavior of the polynomial functions. Okay, now we could sit here and really dive into an exploration, but again, not so ideal of a situation being at home behind our computer. So I am going to give you some notes on this and we're going to look at how it applies. Okay, so I'm actually going to type these out. All right, so we are going to start with if the degree is even. So if the degree of the polynomial is even, okay, the end behavior is the same. If the degree of the polynomial is even, the end behavior is the same. Okay, so I am going to use my red highlighter here, and we are going to find all of the polynomials that are even, and let's look at the end behavior, which is the arrows at the end. Okay, so where's our first even degree? P3. 4 is an even number. Okay, let's look at the direction of the arrows. The first arrow on the back end is pointing up, and the second arrow is pointing up. So those directions are the same, up, up. Okay, now let's go ahead and look at our next even degree, which is P5. What do we notice about the first arrow at the back end at negative infinity? It's pointing down, and the second arrow is pointing down. So they are both the same direction. In this case, it is down, whereas in P3, it was up, and that's okay. Okay, now I'm also just going to go ahead and point out, see this negative right here at the front? Okay, what did a negative do in all of our other functions we've worked with in Algebra 2? Reflected it over the x-axis. So if we think about a normal, I'll call it normal, polynomial that doesn't have a negative and is even degree, will probably be pointing up, up. But that negative out front is going to cause the direction to be down, down. Okay, now on P6, that fourth power is also even. I notice there's no negative out front, so once again we're back to up, up. On P7 is an even fourth degree. There's no negative on the 0.2, up, up. Okay, and then finally on 8, again, no negative on our leading term, up, up. Okay, so the normality of an even degree polynomial is going to have both arrows pointing up. Think about a quadratic to the second power. That would be second degree. 2 is even. Where do both of our arrows point on a normal parabola? Up, up. Where do both arrows point on a downward parabola? Down, down. Okay, so that is even degree and behavior. But now we have to talk about, let's do a different color here. We have to talk about if the degree is odd, and you've probably guessed it by seeing if the degree of the polynomial is odd, the end behavior is opposite. Okay, so on this we are going to use orange. So if we have an odd degree, whoops, I want orange for my highlighter. If we have an odd degree, the arrows are going to be opposite, which you can see right above what I typed out with those blue arrows. Okay, so let's go back in our picture to check that this is true. And if we look at P sub 1, the first arrow points down, the next arrow points up. On P sub 2, 3 is an odd degree. The first arrow points down, the last arrow points up. Now if you think of cubic functions, which was a function we studied in first semester, what does the cubic function look like? The cubic function is an odd degree, and it looks like this. The first arrow is pointing down, and the second arrow is pointing up. So I think that when we have an positive number out front, it's going to follow the trend of the first one pointing down, the second one pointing up. Okay, so let's see maybe if there's a different example of where it switches, but for now let's look at P4. P4, 5 is odd, so we see that our backmost arrow, which is considered negative infinity in the domain, is pointing down, and the next one is pointing up, so they are opposites. Okay, and those are only 2 or 3 examples there. So we didn't see an example of where it flips, but I'm telling you, if the leading term is negative, then it's going to be up and down rather than down then up. Okay, so the big question is, which form of the polynomial equation is most useful for making a graph? Okay, now we haven't done a ton of this yet, but if you think back to yesterday's lesson, when were we able to make somewhat of predictions about the graph rather than just immediately turning to the graphing calculator? Well, that was when it was in factored form. So we definitely want to be given equations that are in factored form, because what can we do with factored form? Okay, well, we can right away, this was yesterday's lesson, determine those x-intercepts, because we can use ZPP by making our mini equations. What can we also do? We can also still determine the degree of the polynomial. And so then what does that allow us to do? That allows us, if it's even, then the end behavior is going to be the same. If it's odd, the end behavior is going to be different. So that leads us into being able to look at end behavior. Okay? And then finally, we haven't completely seen how we're going to do this, but when it's in factored form and we know the degree of the polynomial, we can also look at the orientation. So orientation, okay, is basically related to, is the leading term positive or negative? Okay, so that is kind of relating to, for our, and I might be getting a little ahead of myself, but for our even degreed polynomials, okay, if we have a positive end behavior, then we're going to have up, up. But if we have negative leading term, we're going to have down, down. Okay, so the orientation would be flipped if it's negative. And then for odd functions, if it's positive, the first arrow is going to be down and the second arrow is going to be up. And if it's negative, the first arrow is going to be up and the second arrow is going to be down, because the orientation has been flipped, is what we say. Okay, so that's kind of a little bonus material. So now what we're going to try to do, this is kind of the main point of 811, is we are going to go ahead and use kind of the concepts we just came up with to go ahead and try to sketch graphs of these without a graphing calculator. Okay, now the scale that we draw on the y-axis is not going to be to scale when we view the graph, and I'll explain that here in a second. But if I look at A, okay, I'm going to go ahead and make my axes. And the first thing I want to decide is, what is the degree? I'm going to use D to stand for degree. This is the third degree because I have three factors, none of which have exponents. Okay, so I know that the end behavior is going to be opposite. EB can stand for end behavior. Okay, now if I look, what are my x-intercepts? My x-intercepts in this case are going to be -9, -6, and 10. Okay, we're solving those mini equations, and I'm actually not going to show that work. So I have -9, I have -6, and then I have +10. So those are my x-intercepts if I want to go ahead and plot those. 1, 2, 3. Okay, now if we look at the equation, there is no negative out front on some sort of constant. Okay, so it's going to be normal third degree or odd degree end behavior, which if we think of, I always think of the cubic parent function. It starts with a down arrow and ends with an up arrow. Okay, so we are going to go ahead and sketch in a graph that shows the general shape. Okay, we have a peak between -9 and -6 and a valley between -6 and 10, and we're trying to kind of use our knowledge of symmetry. And the big thing that I would be looking at if I were grading an assignment is that your end behavior matches what the equation tells us. Okay, so if, I'm not going to do this for every problem, so don't worry, but if I plug this into a graphing calculator, your viewing window is -10 to 10, keep that in mind, or if I type it into Desmos, okay, this is what I might see, and I can even zoom in to show what you would see on your kind of graphing calculator, okay? So you just see lines. But keep in mind that if we were to multiply this out, you would do 9 times 6 times negative 10. That's a monstrous number. Okay, so if I zoom out, zoom out, zoom out, you can see that there is a peak to the left of the y-axis, which we drew that. But then look at how far I'm scrolling down. I'm down to negative 600, negative 700, negative 750 is approximately where the valley to the right of the y-axis is. Okay, so if we look back on our graph that we drew, this bottom of the valley should really be way down here. Okay, but we're not really concerned at this point with how far up the peaks and valleys are from the x-axis. We're mostly concerned with the general shape, the end behavior, and the x-intercepts at this point. Okay, so now let's go ahead and move on to our next problem. We can draw in our axes and think about what is the degree. The degree is 4. We have 4 factors. And then what is our end behavior? Our end behavior, because it's an even, is going to be the same. Okay, so we have the same end behavior, and because there's no negatives, we think of the parent graph of a parabola, which is straight up in both directions. So let's go ahead and draw in our intercepts and then utilize the end behavior. So we have negative 5, negative 3, positive 4, positive 8. Negative 5, negative 3, positive 4, positive 8. Okay, now if you look back on the front, most of the 4th degrees were like a W, okay? But we've got to think about how are we going to have our end behavior point upward at both ends, at negative 5 and 8. So when I draw in the graph, okay, I'm going to have a valley and then a peak and then a valley and up. Now again, we don't know how high up the peaks and the valleys are, okay? If we look at the graph one more time, this is the only other one that I graphed. Let me take the red off. Okay, remember I'm way down at, oh goodness, my scale's the thousands right now. Okay, so look at the graph again. Like I see a valley at negative 100. I see another valley. I'm scrolling at negative 410. Okay, so the scale on the y-axis is not accurate when we do these sketches. Okay, so you can pause me if you want to try some of these on your own. That might not be a bad idea, and then see if you're catching on. Okay, good. Check for understanding. So on this next one, our degree is what? Our degree is 5 because that x out front counts as a linear factor. So we know that the end behavior is going to be opposite, and I don't see a negative as my leading term that would affect the orientation. So like my normal cubic parent graph, I have down and then up. So at this point, I'm going to look at my x-intercepts. Now, please do not forget this guy out front here. He counts for ZPP. So the x-intercept here is going to be x plus 0 equals 0. So x equals 0 is an x-intercept in this case. Okay, and that's due to the x out front. Then I have, so I'll put a 0 there. Then I have my negative 3. Okay, then I have positive 4, I have positive 9, and I have positive 15. Okay, so from here then, I'm thinking about my first arrow needs to start down, and then I'm going to kind of go back and forth between my peaks and my valleys. So I have a peak, I have a valley, I have a peak, I have a valley. And if you notice, my first arrow is shooting down, my second arrow is going up, and there's that opposite end behavior. All right, 3 more. So now, okay, we are going to determine what is our degree. Our degree is 4. What do we notice on this one? We have a negative. So even though my end behavior is going to be the same, the negative switches the orientation. It flips that parabola that we're thinking about or relating to. So both of my ends are going to be negative. Okay, so my first y-intercept is going to be -5. Then I have -2. Then I have +4. And then I have +10. Okay, now to make my graph, I am going to start thinking about an arrow that would shoot down. And then I'm going to have my peak, my valley, my peak, and what's it going to end with? Pointing down once again. Okay, so we have the same behavior, but in this case, the orientation has switched. All right, now we come to E. On E, what is something new that's coming up on this problem set? We have a factor being squared. So first and foremost, what is the degree of this polynomial? Well, we have this guy right here because there is a variable. So we have 1, 2, 3, 4 because you've got to count the second power. All right. So we don't see a negative, so our end behavior is going to be the same. And in this case, because the orientation doesn't flip, we have up, up. So now I'm going to go ahead and look at my x-intercepts, which again, if there's just an x sitting by itself, that is the x-intercept of 0 and it has to be included. If you don't, then you're going to be confused as to how you're going to get the proper end behavior. And then I have -1, and then I have +3. Okay, but we can't ignore that the +3 x-intercept has a power of 2 that is attached to it. And if you look back at yesterday's notes, I talked about kissing the x-axis. When there is an even power that is attached to a factor, the valley or the peak is not going to, or sorry, I should say, the curve is not going to cross the x-axis at that point. It is going to kiss, making it the peak or the valley of a minimum or a maximum. Okay, so what I'm going to do is I'm going to start thinking about my end behavior, which is going to be here, and I'm going to do my normal curve down, my normal curve up. But watch what happens. When I get to 3, I don't cross. I kiss the x-axis and change direction. Okay, so this is very important right here. I did not cross the x-axis. I changed direction and kissed the x-axis. Okay, other people might call it just touching, bouncing. Okay, that's what we're going to use here in a little bit when we kind of make the wording. All right, one more case to talk about. So in this one, we have an exponent of 3. So that is an odd exponent. So something a little different is going to happen. But let's first determine the degree. So the degree, we have an x out front. So that counts as 1, 2, 3, 4, 5, because we've got to count that 3 times. Now, because we have an odd degree, the end behavior is going to be opposite. But the negative out front, okay, is going to cause us to think opposite of the cubic parent function. So the first arrow is going to be up, the second arrow is going to be down. So I'm going to draw my axes in and see that right away my first factor, if I set -2x equals to 0 and solve, I'm going to get x equals 0. So that is an x-intercept. And then I'm going to get x equals -1. And then I'm going to get x equals +3. Okay, and my end behavior has to start with an up arrow. So I'm going to do my normal valley, okay, peak. And then how am I going to get it so that I continue in the downward direction? Okay, so what I see here is when I have an odd power attached to an x-intercept, I am going to flatten out is what we call it, and then continue in the same direction. So we are not kissing when it is a odd exponent. We are flattening out and then continuing in the direction that we were already traveling in. Okay, so again, that is very important, that that odd exponent means that we are going to flatten out. So, with that being said, okay, through these 6 examples, we're going to take some very important notes. I'm going to type them in, make sure these are clear. So, based on the graphs above, let's answer the following. What part of a factored equation causes the graph to turn or bounce at the x-intercept instead of cross? Okay, well, that is example, we can write that right in, that is example E. Okay, and let's type out what we have established, that when the degree of the linear factor is even, that is when it is going to kiss. Okay, so I'm going to maybe write that keyword in. Bounce, what have I been using in my lessons? I've been using the word kiss. Okay, so what does that look like? That is going to look like something that just touches that axis rather than crosses it completely. Okay, so there's our first key point. Now, number 2 says, what does an odd exponent that is greater than 1, okay, that is important, on a linear factor due to the x-intercept? So example F is where this is really talked about. Okay, so we are going to say that the graph flattens as it crosses the x-axis. So it still is going to cross if it's odd, okay, but it's going to flatten as it crosses. So there is going to be some change in shape. So that is key. Now, when is this going to happen? This is going to happen when we have exponents of 3, 5, 7, and so on a given factor. Okay, so what is the end behavior of an even degree polynomial? Okay, so if we have an even degree polynomial, we know that both are going to be the same. Okay, so we see that, again, I think I said this on the last slide, if we have if it's normal, if it's positive, okay, just like x squared, we are going to have up, up. So we are thinking about a parabola when we're working with even exponents, okay? But if it's negative, then we flip that parabola or whatever other shape we're thinking about, okay? But then if we are odd, then we know that it is going to be opposite directions. And instead of just trying to blindly memorize this, I'm going to think back to my parent cubic function. So if we're positive, then the first arrow is going to be down, the second arrow is up. But if we're negative, the first arrow is going to be up, the second's going to be down, because we would have to flip. Okay, and then finally, our final key point is, how does changing the exponent on one of the factors change the graph? So for instance, what this question is saying is, let's say that we had, like x plus 3 times x plus 2 times x minus 1. Okay, what if I all of a sudden introduced a second power here? Okay, is that going to be a big deal? The answer is yes. Okay, so what first would happen? Well, it would change the degree. So it could change the degree. Whoops. And when the degree changes, what is that going to cause to change? That is going to cause the end behavior, or could cause the end behavior to change, and that's a very big deal. Okay, also, what could happen? The shape could change. Okay, so another thing that could change is the shape of the graph could change. And why is that? All of a sudden, the graph may, let's see, the graph may bounce or flatten rather than just cross. Whoops, I don't know what's going on here. Okay, sorry, it got a little messy there. So if we change an exponent, such as adding a 2 onto one of the factors, that is going to be a huge deal. The degree could change, which would cause the end behavior to possibly change. And then looking at that particular factor, the graph would suddenly just kiss, meaning bounce, or flatten out, rather than simply cross the x-axis at a given point. Okay, so you've got to be very careful and pay close attention to the details or every detail of an equation when you go to think about the general shape of that given polynomial. All right, so that concludes 811. There are a few more homework questions that I'm asking you to do from the same section tonight, and we will continue with 812 on the next lesson.